Okay, so what we're going to talk about today is going to be something to sort of tune your eye to. Because, look, when you're trying to compute an antiderivative function, when you're given an integral, and we've got a bunch of integrals here on the board, your task is to find the function whose derivative is the function that you're given. And now, those functions tend to come in a few forms, and what we want to do is to sort of, again, tune our eyes to recognize when to use what. So sometimes you get a function that is really just an application of cookie cutter formulas. Because, oh, the 4x squared, that's fine, set the 4 aside, 1/3 x cubed, put the 4 back in. Here we've got things separated with plus or minus signs. You've got a 5 constant multiple, take the constant multiple, set it aside, 1 over 1 plus x squared, that's inverse tangent. Put the minus 5 back in, no sweat. Take the 10 out for a second because that's just a constant multiple is unaffected by integrals. Secant tangent, that is antiderivative. The function who has a derivative of that would be secant. So, that last bit is just 10 secant plus secant. That's sort of a cookie cutter formula expression. Nothing too crazy. Take the constant multiples, factor them out, keep track of your pluses and minus signs, use your cookie cutter formulas for x to the n, for inverse tangent, for secant x. Okay, the other situation that popped up, and the other situation that you've seen a lot of examples of, is applying u substitution. So what if you have an integral that whenever you look at it, it involves multiplication, and it involves 2 bits of your expression related by derivative. Like x cubed minus 7 and 4x squared. Now you say, but wait a second, 4x squared is not exactly the derivative of x cubed minus 7, but that's fine because you can always adjust for a constant multiple, and you can make this integral work. But the long story short is whenever you're doing u substitution, you're looking to see 2 bits of the expression related by derivative. Actually, this sign ln x over x is such an example because you've got the ln x, and you know the derivative of ln x is 1 over x, so that's going to account for that x downstairs. But now what I want to bring to your attention is a key and important note. Okay, while we can directly apply our cookie cutter formulas, and while we can use u substitution to undo the chain rule, because the u here, what we're doing in effect, is looking at integrals of the form f prime u times u prime. We have no formula, though, to undo the product rule, or the quotient rule. Note, there is no corresponding product or quotient rule for antiderivatives. Like, you know that whenever you take the derivative of a product, you just use what u v prime v plus u v prime, whatever. You know that whenever you have a product, you use, or rather a quotient, you use the quotient rule. But there's no such thing for antiderivatives. You'll see in Calc 2, if you go to that level, there is some antiderivative technique that applies the product rule, but it's not the product rule directly. So there's not some cookie cutter way to deal with products. And while yes, u substitution sometimes has something that looks like a product or something that looks like a quotient, really every u substitution integral is based on this f prime u prime. Okay, so now how do we take this knowledge of what we've been exposed to at this point? Okay, we got cookie cutter formulas, we got u substitution undoes the chain rule. Well, we can undo the chain rule, we can undo the cookie cutter formulas, but there's nothing to undo the product rule or the quotient rule. There's no such thing for antiderivatives. Well, what if you have an integral involving multiplication? Because I claim when you have an integral involving multiplication, there's one of 2 things that could be true at this point. One is substitution applies. What you're seeing with multiplication is the f prime u times the u prime. The other possibility is that u substitution doesn't apply, and then we can't apply some product rule, we just have to first multiply before doing the integration. So take a look at these two integrals, because one of these two integrals is tailor-made for u substitution. What about this guy? U cubed minus 7, 4x squared. You can see directly, yes, there is multiplication involved, but that multiplication is a part of f prime u times u prime. Because we've got our u here, we've got our u prime, we're going to set u equal to x cubed minus 7, and then proceed through the problem. du, 3x squared dx, so on and so forth. But the long story short is, this type of problem is something that we would have seen, could have seen, very well might have seen previously whenever we've been working u substitution integrals. But what about this guy below? When you look at him, yes, he involves multiplication, x times x squared minus 4. But whenever you ask yourself, is this u substitution? Is this an f prime u times a u prime? Are there two pieces of this function related by derivative? The answer is certainly no. Because if you set u equal to x minus 4, what do you do with the x? And if you set u equal to x, what are you going to do with the x squared minus 4? The x and the x squared minus 4 are not related by derivative. So now if we don't have two pieces that are related by derivative, if we can't use the u substitution, if we can't use the chain rule, then it's like, oh wait, what do we need? Do we use the product rule? Well, there is no such thing. So how do we proceed? And the answer is, if you have multiplication and it's not the chain rule, just multiply first. Because you see, if you do the multiplication, you can literally multiply x times x and x times minus 4, and you'll get x squared minus 4x. Now, you haven't done an antiderivative here. You haven't applied the integral. You've just taken what the original function was and you've multiplied it. But now this is totally doable, right? 1/3 x to the cube minus 2x squared plus c. If you have a function which involves multiplication and it doesn't involve u substitution, just multiply it out. You don't have a product rule. Since you don't have a product rule, just use the product and then see what comes out and apply the antiderivative to that. Because trying to find the antiderivative function from here is almost impossible to see, but once you multiply it out, it's like, oh, I can see exactly what the antiderivative function is. Okay, what about integrals involving division? Here, we've got an integral involving division. Now, this integral involving division, I claim, is actually subtly an integral almost involving multiplication, because you can see that this is going to involve u substitution because, well, take a look. You've got an L and X, you've got an X in the denominator. You know those relate by way of derivative. When you see an integral involving division, both of these involve division, what should you do in your mind? You should ask yourself, does this involve u substitution? Because if the answer is yes, then use u substitution. If the answer is no, then just divide. This guy is really, in effect, integral of sine ln x times 1/x dx. Now it's really easy to see that this is a u substitution integral. We're going to set u equal to ln x and proceed. Problem solved. Well, we didn't actually solve it, but you know that you could. What about this guy below? When you look at him, is this a u substitution integral? Now, when you think, oh, maybe this is a u substitution integral, maybe I set u equal to 7 plus 2x plus 5x squared, because I've got a degree 2 bit and a degree 1 bit. But the issue here is that whenever you compute du, you end up with 2 plus 10x. How are you going to convert that into x? Because we're going to have, like, all you can do here is multiply by a constant. If you want to multiply by 1/10, that's fine. You can multiply by 1/10, but you're still going to have a 1/5 in front of your x, and that doesn't jive and work. So if u substitution is not going to work here, yet we involve division, what do? Do we use the quotient rule for antiderivatives? Ah, there is no such thing. So what do we do instead? We just divide. We just go 7 over x plus 2, the x's cancel there, plus 5x. Look at that. No sweat. 7 ln x plus 2x plus 5 over 2x squared plus c. If you have multiplication or division, first check, does U substitution apply? If U substitution doesn't, just multiply, just divide, proceed.